So this is something that's quite interesting and new, because many of you probably heard about such elements as resistors, inductors, or capacitors, but memristors are kind of a mystery. But nevertheless, in 71 already they were discovered because of some completeness of relations between some such quantities as voltage and current. And the question is, okay, so can we make such elements in quantum domain? That means that can we make a quantum resistor, inductor, capacitor? Obviously, these are easier questions to answer than this one, and the answer is positive for each of these. But the problem with quantum memristor is that your classical characteristics, this IV curve, is actually looks like a bow tie with this pinched hysteresis here. And if you have a look at what is done in the literature, usually this is classical, let's say, hysteresis for classical device, and it's compared against quantum counterpart. Okay, and so this is one way of making quantum memristor, but I think that it's better to start to go with this hysteresis, and it has this. So to have a memristor, you have to have this kind of behavior, and also this area of this hysteresis should shrink with the sweep frequency. So if you change current from maximum to one and to another, you should observe this. If you do this faster, you should basically see no memory. Okay, so this actually can be done in a different way, but it demands some changes in way of thinking, because that approach, as I referred you to, was actually based on density matrices and measuring things, and it's a kind of like measuring photon numbers, not relying on quantum fields on their own. So so what we will do here? So here we actually use some standard bricks. So we apply unitary operation. The only thing that is actually non-standard is that that we apply memory parameter theta here. And this memory parameter is updated according to this equation. So here is the coupling strength, here is some measured quantity, and here is relaxation. Okay, so and this is equilibrium position. So this actually tells you about the memory of the system. So it will be clear from the pictures very soon. Okay, so these are detection events, feedback strength, and relaxation rate, equilibrium angle. Fine, and this is the idea, the total architecture that I will try to convince you that it's kind of a way of doing quantum to memristor in a very easy way. You take a qubit. You imagine that you have a train of photons, because they will have to be destroyed. But if they're not destroyed, then this could probably work with several qubits, and you just rotate it or apply unitary operation on it. You have some output state, you measure the state, you perform classical feedback, you compute this parameter, and you apply control. Okay, that's it. Basically, this should exhibit this kind of hysteresis if this is properly done, if this is proper unitary operation, and you measure proper thing, and you should be able to recover this bow tie shape. Okay, and you can do this with photons. This is mature technology. You can encode 0 in horizontal and 1 in vertical polarization state. You can apply a half-wave plate transformation with this theta angle. Actually, it turns out to be like probably the best way of doing this. And if you prepare such a simple device, okay, and you will just feed this to some FPGA and some probably liquid crystal based have HWP, you will be able to get the behavior that we want. Okay, so but this actually means that photon is destroyed. So at some time you just create photons from the source at the constant rate. Okay, so this is probably this will work with special choices of these parameters. I admit that this is a very idealized case, but you will measure v, probably h at some point, v and h, and you will feed this information to the next photon, and you will change this theta angle of your wave plate according to this update rule. Okay. And this update rule actually gives you also a kind of idea how to go to fully coherent quantum memory store, because for now this is just classical memory. This is stored in some parameters, computed and applied here. But if you perform like such procedure for photons, and you will repeat this several times. You can average it because you will have just basically like single quantum trajectory. So you have to repeat this many several times to get this kind of shape. You will see that you obtain some hysteresis, and basically if you change input polarization, you will sweep this input polarization. You will get this shape. Okay, this is steady state because it does not start with the steady state. You have to wait for like 10 cycles to get the steady state. And if you have no memory, you just have fixed angle on your HVP. You get this just uh, 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 just a rotation. Yes, basically. So this pinched hysteresis, I think, is very important characteristics of Memristor. Also, different paths for increasing, decreasing input. You should be able to see this. I go this way, I change direction, I go this way. So this is hard to observe in other. Say ideas about memory stores, because there are like loops here, and you don't see the change in direction depending on the direction of sweeping the field. Okay. And basically, you can solve this equation analytically. You can see what's the result, what's the dynamics, and you also can analyze what's the area. Basically, what's the memory. Okay, so so if you run the simulation, this is input polarization. This is dashed black curve. The blue solid curve is output polarization. Uh, by first I go like this, and you see that something happens in time. And also this each WP angle also changes in time. It oscillates because of this if you sweep the input. And you will observe this frequency dependence. So you, depending on the rate at which you sweep this polarization, you'll have different curves for your hysteresis. And this is major characteristics of Memristor. So this should be visible. Okay, so there were some previous works on quantum memory stores, and very nice. This is the most recent one. The paper is on archive since March, but there is still no pinched hysteresis. This is just like the loop that I try to convince you that it's not enough to say that it's quantum memory store. Okay, and there are some advantages in our proposal. And I think that this is very interesting topic. You should think about going into this, because it has many potential applications, including feedback enhanced sensitivity, or adaptive measurement strategies, or applications to quantum computing or machine learning. So in the long run, I think this will be very important to understand what is the quantum counterpart of the memory store, and moreover to actually use quantum memory for this. So this means that basically I have a wave plate that is in superposition of two angles instead of just one wave plate. And this can be achieved just by taking the input and looping it in this way. So this is controlled unitary gate. We wrote some paper about it some time ago. So this can be implemented with optics. The trick is to synchronize the input-output from the next photon in the train. And if you do this twice, okay, there is no memory here, unfortunately. So it's not enough. You have to do this nonlinear response. So if you put this first photon goes here, next photon, actually the same photon circles second time, and the first time it's the control photon, second one is the program photon. So it gives you this kind of update to your theta that becomes theta dependent, okay? And this allows you to recreate exactly this update rule for measurement dependent situation. Okay, so this looks complicated, and it is because we tried to construct something which we called quantum router some time ago, and it actually at its heart there is a component that will be essential for this implementation if you attempt to do this. And this is where I wanted to conclude. So this is our idea to this theoretical proposal for photonic quantum memory store at single photon level, and this architecture actually demonstrates all signatures of Memristor, why actually preserves quantum coherence. If you think about like in the end, like having multiple quantum trajectories and measurement-based approach actually enables this programmable memory dynamics. So it means that you can choose the coupling strength, the feedback strength eta, or this decay rate gamma to some extent within your implementation. Okay, so the take-home message is quantum systems can have memory, and yeah, sorry, I think I took too much time, but that's it. Okay, so you're welcome downstairs to ask some questions.
Thank you, Karol. Questions?
Thank you very much for the. I've never heard of this concept, so very nice to hear. You have hysteresis on the quantum side. Would you like briefly like explain why it does like goes like this?
Goes like this. Okay, I have many slides to explain things. Potentially, people could ask. Okay, so
the one on the
your
first one.
input state is this alpha, for example, and this is some polarization state. And what it does, it actually after measurement, it updates this theta parameter, and this in a result. Takes this, let's say, next pair that is measured input-output relation, and it's a next point, let's say, on this trajectory. So this actually first photon has an effect on the next photon that enters this setup. Okay, so so this is the output. So this is first, next photon, and so on. So this is how we analyze this. So so if you would just like have a look from above on this, you would see this hysteresis. Okay, so this is how this hysteresis happens, and this is because we have this formula for computing theta that actually we designed it to form this hysteresis. You could update it using a different rule, then the shape would be different, and this is what you observe.
Basically, the why the hysteresis appears is from which term of theta? Because yeah, I mean you have expression for theta.
Yes.
And which term does it hysteresis is created or originated from?
Okay, so if you okay, I think I don't really get your
Like, is
question.
any analytical form of theta yield
Yes.
a hysteresis? Like any function of any yeah. Maybe you can, yeah, I can.
Yeah, maybe we can talk later because it's already lunchtime. But I'm happy to discuss this during lunchtime. Okay, so
Thank you.
thank you.
Yeah. Why is system with one photon doesn't have a memory?
Photon system with one photon does not have a memory. I'm explaining this. Okay, system. Sorry, I went back too far. This is it. Okay, so this is one photon, and imagine that you have this photon alpha. It enters this controlled, let's say, unitary. Okay, and what happens is that you just set at some time some arbitrary theta, let's say 0, and what happens? This photon just is rotated a bit and goes back here, and it should work as the control for this operation. So this operation will actually again, if it happens, it will update. I mean, the theta is always of this form, okay? Because you cannot distinguish in this way between entries, I think. Okay. The problem is with this update rule, how this original update rule is created. I will go back a bit. Okay, here. Okay, so what you can do with one photon is having this form of update to your theta and this form of update, but you have nowhere to store this information about the current theta. Okay, so so you can just so what happens here, if you just think about it, what happens in this loop, you just each time at each iteration you just do something like this, where this let's say this actually term is not here. Okay, so there is no relaxation. So that's the problem. There is no relaxation to the other mode. So this is so if there is no relaxation driven by this by the current state. So it means that it doesn't remember what was the state in the update rule. So it just has this current state, and this controlled unitary updates it by some constant value. Okay, so this is why you don't have this gamma times theta term minus gamma theta times delta t, because you don't know what to put here. It can be arbitrary number basically. I think that's the best I can explain it.
Okay, if there are no urgent questions anymore, then let's thank Karol again and all the other speakers.